Picture this. You're miles offshore, and the sky suddenly turns the color of, well, a bruised plum.
Oh, that is never a good sign.
Right. The wind starts howling so loud you can barely hear yourself think, and your boat is just violently tossing in the chop.
You're in survival mode at that point.
Exactly. You need to secure the vessel right now. And, I mean, decades ago, this meant crawling up to the pitching, totally slippery bow.
Risking getting thrown right overboard,
Yeah, and physically wrestling hundreds of pounds of cold, wet chain by hand. But today, you are standing safely in the cockpit, a single sailor, calmly pushing a button.
That's amazing.
I don't even break a sweat because you have this powerful, silent partner up on the deck doing the heavy lifting.
It really is a phenomenal image, and it highlights this massive shift in marine technology, because that silent partner you're talking about is the electric anchor Windlass.
Right.
We're looking at a system that has completely revolutionized what is arguably, the single most dangerous routine task on a boat.
Which is exactly what we are unpacking in our deep dive today. We've gathered a huge stack of marine manuals, technical specs, and owners' forums.
Specifically looking at the quick USA models.
Yes,
right?
exactly. To really get under the hood of this machinery, our mission for you, the listener, is to understand the mechanics, the physical operation, and the meticulous maintenance of an electric windlass.
Because when you actually understand the physics and the engineering behind how this machinery works, you realize it isn't just some motorized winch.
No, not at all.
It's a highly integrated system. I mean, it's the very thing that gives a person the absolute confidence to handle a sizable yacht completely single-handed, even in that kind of bruised plum storm you just described.
So let's start by dissecting the anatomy of this thing, because we hear the term windlass tossed around, but if we strip away the shiny outer casing, what are the actual core organs of this beast?
Well, at its heart, you're looking at three main components. First, there's a highly robust gearbox. This is basically the muscle of the whole operation. It takes the high-speed, relatively low-torque spin of an electric motor and translates it into immense, slow-turning torque.
Because you need that slow, deliberate pulling power. Right. To lift all that ground tackle.
Exactly. You can't just jerk it up. So second, you have the solenoid. And you can think of this as the gatekeeper.
The gatekeeper, I like that.
Yeah, it's a heavy-duty electromagnetic switch that safely manages the massive electrical current that the motor needs.
I am so glad you brought up the solenoid, actually, because the why behind it is fascinating.
It really is.
A lot of people might wonder, well, why don't you just wire the helm switch directly to the windlass motor? But we are talking about drawing over 100 amps of direct current.
Which is a huge amount of power.
Right. If you ran those thick, heavy-gauge battery cables all the way from the bow back to the cockpit and then up into your control panel, you'd experience this massive voltage drop over that distance.
Not to mention the safety aspect.
Oh, absolutely. Putting that much raw amperage directly under the captain's fingertips is a massive fire hazard. So the solenoid lets you run these tiny safe control wires to the helm, which just tell the heavy-duty switch up at the bow to, open the floodgates for the main battery power.
That is a perfect explanation of the electrical architecture. I mean, you are fundamentally isolating the danger. And that brings us to the third and perhaps most iconic part of the anatomy, which is the gypsy.
The gypsy is such a specific nautical term.
It really is.
This is the grooved metal wheel on the outside that physically grabs the anchor rod, correct?
Yes, exactly. And the gypsy is a total marvel of precision engineering. It has these specific molded pockets that perfectly match the lengths of your exact size of anchor chain.
Oh, so it's not just one size fits all.
No, it has to be precise. It also features inner grooves designed to grip a 3-strand polyester rope. So it has to bite down on the line to pull it in or let it out without slipping, even when there's, thousands of pounds of tension on it. And when you look at comprehensive models on the market today, like the Quick-LF, for example, they don't just hand you a motor and a gypsy in a box.
Right, it's a whole package.
Yeah, they provide a complete tactical kit. You get a clutch handle to manually tighten or loosen the gypsy's grip, a winch handle for extra leverage, a protective cover, and a wireless remote for mobility.
Now, when a boat owner decides to actually install one of these systems, they hit this major fork in the road regarding the design, vertical versus horizontal.
The big debate.
Yeah. And looking at the specs, this seems like a layout philosophy as much as an engineering one. Okay, let's unpack this. Is a vertical windlass essentially like a sleek, built-in kitchen appliance that saves counter space, while the horizontal one is like a heavy-duty countertop mixer where you can easily reach all the moving parts.
I love that analogy. I mean, it perfectly captures the user experience.
Thanks.
So a vertical windlass operates with its motor and gearbox hidden completely below the deck, basically suspended inside the anchor locker. The only thing you actually see above deck is the Gypsy itself, so it is vastly space-saving. It leaves the deck clear, which minimizes trip hazards.
Which is a huge premium on modern yachts, for sure.
Absolutely. Also, because the chain wraps horizontally around a vertical Gypsy, it creates a 180-degree wrap.
Meaning it grips more chain links at once.
Exactly. It grips more links and pulls incredibly smoothly over the bow roller.
And from a material standpoint, these vertical units are often constructed with anodized aluminum, right?
Yes.
So they use this electrochemical process to build a really thick protective oxide layer on the metal, which makes it incredibly resilient against all that saltwater spray up on the bow.
That's exactly the kind of defense you want up there. But, the major trade-off for that sleek profile is accessibility.
Right, because everything's hidden.
Yeah, because the motor is below deck. Checking on it or servicing it requires you to physically climb down into this dark, damp anchor locker.
Sounds awful.
It's not fun. A horizontal windlass, on the other hand, sits entirely above the deck. The motor, the gearbox, the Gypsy, it's all housed in one unified casing right on top of the fiberglass.
So it requires a lot more visible deck area.
It does. And you have to ensure the chain has a straight, totally clear run from the bow roller right back to the unit.
Meaning it's fully exposed to the elements all the time?
Yep.
So even though it's built from durable marine-grade alloys, if it's constantly taking salt water over the bow, it could corrode much faster if you aren't really diligent.
Oh, without a doubt.
But the flip side is that if something goes wrong, the entire mechanism is just sitting right there in front of you.
It's the classic engineering compromise. You basically trade deck space and weather protection for immediate, easy access to all the moving parts. You can just visually inspect the supply cables and the motor casing without contorting yourself through some tiny hatch.
Thinking about those hidden components on a vertical setup brings up an interesting point about vulnerabilities, I think. Because once you've chosen your layout, the secret to a stress-free anchor drop doesn't magically happen when you push the button at the helm.
Not at all.
The success of the drop is determined long before the anchor ever touches the water. The forums we reviewed are just adamant about this first line of defense, which is meticulous preparation and inspection.
The irony of a windlass is that it's this incredibly strong tool, capable of lifting literally thousands of pounds, yet its reliability entirely depends on the smallest, weakest link in the system.
And according to the technical manuals, that weakest link is very often the splice.
Yes.
For anyone unfamiliar, most recreational boats use a combination rode. They don't use 300 feet of heavy chain, because that would put way too much weight in the bow.
Right, it would cause the boat to pitch terribly in the waves.
Exactly. So instead, they use maybe 50 feet of chain connected to 250 feet of really thick nylon rope. The splice is the literal physical point where the flexible rope is interwoven into the final link of the heavy metal chain.
And that splice is a critical failure point. That transition from rope to chain has to pass smoothly through those tightly engineered pockets of the Gypsy we talked about earlier.
Right.
If it's a weak splice or a bulky splice, or if it has even a tiny frayed edge on it, it will jam.
Wow.
And it won't just jam when you're safely testing it at the dock. It will jam exactly when the windlass is under heavy load in that bruised plum storm we talked about, right when you need absolute control.
So if that splice is the weakest link, and you're dealing with hundreds of feet of heavy, wet line, how on earth do you reliably inspect it? You can't just glance at it in the locker and assume it's going to feed properly under thousands of pounds of pressure.
No, you have to inspect it under tension,
Right.
Which is where the wireless remote, like the one included in the quick kits, becomes just invaluable.
Oh, that makes sense.
Yeah, you walk up to the bow, you stand a safe distance away, and you use the remote to slowly inch the chain and the splice right through the Gypsy. You're actively observing how it articulates.
You're looking for a seamless transition.
Exactly. If it catches or hesitates or forces the Gypsy to kind of skip a beat, you redo the splice at the dock. You do not wait for it to fail in the field.
So what does this all mean for the everyday sailor? Does it mean treating the anchor locker like the engine room of the ship? Because the forums talk constantly about treating the locker like an active mechanical space, not just a wet storage bin.
It absolutely requires an engine room mindset. Before a trip, you need to clear out any mud, sand, or, seaweed that the chain dragged in during the last trip.
Right.
You have to ensure the drains at the very bottom of the locker, they call them the weep holes, are totally clear.
Because of the water.
Yes. Standing water in an anchor locker is a death sentence, especially for a vertical windlass motor suspended down in there. The water just evaporates, creating this highly corrosive, humid sauna that slowly eats away at the motor housing and all the electrical connections.
And I would add that you also have to check the actual physical amount. I mean, you are transferring massive kinetic energy from the movement of the entire boat through the relatively small footprint of the windlass right down to the seabed.
It's an immense amount of force.
Yeah, so if you have loose bolts, or if you see tiny spiderweb cracks in the fiberglass around the mount, that is a massive red flag. Under a heavy storm load, a compromised mount means the windlass could literally get ripped right off the deck.
A catastrophic failure you want to avoid at all costs. And alongside the mechanical prep, the electrical safety checks are just totally non-negotiable. The circuit breaker is your primary safety net. You have to ensure the breaker size perfectly matches the windlass capacity.
Let's actually talk about the physics of why that breaker is so important, because it's not just a simple on and off switch.
No, it's not.
An electric motor relies on spinning to regulate its own power draw. So if the windlass gets physically jammed and the motor stops spinning, the resistance drops, and it instantly starts pulling massive, surging amounts of current from the batteries to try and break through the jam.
Which is incredibly dangerous.
Right. That current spikes the heat in the wiring instantly. So if your breaker is too large for the system, it won't sense the danger, it won't trip, and your wires will literally melt and catch fire. But if the breaker is too small, it'll pop every time you try to lift even a slightly heavy anchor.
It's a really delicate balance. The system needs room to work, but it needs a strict sealing to prevent a complete meltdown. So you must visually inspect the wiring for any signs of heat damage and physically test that breaker before every single trip.
Okay, so let's say the locker is pristine, the splice feeds beautifully, the breaker is perfectly rated and tested. We head out, we find a stunning, secluded cove, and it's time to deploy.
The fun part.
Exactly. Now, instinct might tell a novice that dropping an anchor is just, hitting a button and letting gravity rip. But based on the operational manuals, it is an absolute art form requiring a lot of precision.
It requires significant finesse. And the beauty of these automated systems is that they allow you to manage that art form right from the helm.
Right.
For a solo sailor, this fundamentally changes the game. You no longer have to abandon the wheel and sprint up to the bow. You maintain a clear 360-degree view of your surroundings. You have one hand on the engine throttle to control your drift, and you're positioned in the safest, most stable part of the boat.
And when you're standing there and you hit the down button, the control circuit actively manages the power flow. It doesn't just physically disengage a brake pad and let the heavy chain fly.
No, that would be chaotic.
Right. It uses the electric motor to power the chain down smoothly, which prevents those massive sudden jerks that can severely damage the gypsy or just shatter the bow roller.
It provides steady, metered control over a very heavy and very dangerous load.
But here's where it gets really interesting, and I want to push back on a common misconception here. Because if I'm out there, my engine suddenly dies, and the wind is rapidly blowing me toward a rocky lee shore, every instinct in my brain screams to drop that hook as fast as humanly possible to grab the bottom before I wreck.
Naturally, yeah.
But the quick manuals are explicit. Lowering the anchor slowly and deliberately is actually the safer, more effective move. Why is speed the enemy in an emergency?
It really comes down to fluid dynamics and basic physics. Speed creates chaos on the seabed. If you disengage the clutch and just let a heavy chain free fall through the water column, it doesn't lay out in a nice, neat little line on the bottom.
Right.
It falls faster than the boat is drifting, so it just piles up directly on top of the anchor in this massive, tangled heap of metal.
It's like dropping a heavy steel necklace into a teacup. It just instantly knots itself up.
That is exactly what happens. And when your boat is finally pushed back by the wind and the line pulls tight, that piled up chain fouls the anchor.
Oh, I see.
For an anchor to work, it's flukes. The pointed metal blades designed to bury themselves into the sand or mud, they need to be clear. If the chain wraps around those flukes, the anchor can't dig in. It just becomes this useless, heavy lump of metal skipping across the rocky bottom while you drift closer to the shore.
That is terrifying.
It is. Furthermore, If you free fall the chain and then suddenly panic and hit the brake, the kinetic energy of hundreds of pounds of metal snapping tight, that can literally tear the windlass right off its mount or just snap the chain outright.
That makes total sense. Slow and deliberate actually wins the race because you are establishing proper geometry. The manuals talk a lot about scope, right?
Yes, scope is crucial.
Which is the mathematical ratio of the length of deployed chain to the depth of the water. So if you are in 20 feet of water, you might deploy 100 feet or even 140 feet of chain, giving you a 5-to-1 or 7-to-1 scope. You do this because you need the chain lying perfectly flat on the bottom, pulling horizontally on the anchor shaft so the flukes dig deeper into the earth. If you just drop 20 feet of chain in 20 feet of water, the boat will pull straight upward and just pop the anchor right out of the mud.
The geometry is everything. The proper technique is to pay out enough chain to reach the bottom, and then as the wind or your engine slowly drifts the boat backward, you continuously pay out line to lay it completely flat.
Right.
Once you have your 5-to-1 scope, you put the boat's engine in reverse very gently to actively dig those flukes deep into the seabed.
And throughout this entire drop process, you have to be hyper-aware of tension. You need to actively listen to the pitch of the electric motor. If it starts groaning, you're straining it.
Yeah, you really have to listen to the equipment.
But you also have to aggressively avoid slack chain in rough weather. Because if a wave lifts the bow while the chain is slack, the boat falls down the back of the wave and the chain snaps tight with devastating structural force.
Yes, the snatch load.
Right, a snatch load, and it just destroys hardware.
Yeah.
You use the windlass to keep the tension steady and balanced as you deploy.
And, listening to the motor groan under a smash load brings up a terrifying reality about all this. We are taking highly sensitive electrical and mechanical gear and basically bolting it to the bow of a boat in one of the most hostile environments on the planet.
Saltwater.
Yeah.
The ultimate destroyer of machinery. Which means maintenance isn't just a weekend chore, it's a survival tactic.
Saltwater is totally relentless. The silent, constant threat is corrosion, specifically galvanic corrosion, where dissimilar metals react to each other in saltwater. Routine maintenance on these systems is entirely about battling that intrusion.
What does that look like practically?
It means rigorous cleaning. After every trip, you must wash the gypsy and all visible metal components with plenty of fresh water to dissolve the salt crystals before they pit the metal.
Okay.
And you have to regularly lubricate the clutches and the gears precisely according to the manual's timeline. This prevents the metal surfaces from just seizing together and avoids sudden mechanical lockups.
And the electrical side is equally vulnerable, right? Because the motor is living its life in this high humidity, incredibly salty environment.
Absolutely.
You mentioned earlier that loose bolts are bad for the mount, but loose electrical connections are just as dangerous. A loose wire joint increases electrical resistance. Resistance creates heat. Heat melts insulation and causes catastrophic failure.
It escalates very quickly.
Yeah. So you have to routinely check for burnt marks on the wire jackets and clean the electrical contacts to prevent arcing.
Let's put this into a real-world scenario for a second. You are out on the water, you go to retrieve the anchor, and suddenly you hear this horrible metallic grinding noise coming from the windlass. What is your immediate reaction?
Well, if a listener is out on the water and hears a grinding noise from their electric motor based on the safety protocols, the very first thing you do is take your finger off the remote button. Stop the windlass immediately.
Stop it right then.
Do not try to force it to power through the problem. But I wouldn't just hit the emergency breaker as a reflex either, unless I smelled smoke or suspect an electrical fire. A grinding noise is mechanical. The motor is trying to turn, but the gears or the chain are physically binding up.
Spot on. So if you have a massive, heavy chain physically jammed in the gypsy, how do you go about untangling it without losing your fingers in the process?
Yeah, that's the scary part. The golden rule of any jam on a boat is you release the load tension before you ever try to put your hands near the machinery.
Crucial step.
That chain is being pulled incredibly tight by the entire weight of the boat drifting in the wind. If you pry at a jam chain with a screwdriver while it has 1,000 pounds of tension on it and it suddenly pops free, the gypsy will violently spin and take your hand right off.
It's incredibly dangerous.
You have to transfer the load. And for anyone who isn't a seasoned sailor, you do this using a deck cleat. That T-shaped metal fitting bolted directly into the structural fiberglass of the hull. You take a secondary line, tie it to the chain, and secure it to the cleat so the hull takes the physical strain of the boat, not the windlass gears.
Exactly.
Only then do you use the clutch handle to loosen the gypsy, untangle the bind very slowly to avoid tightening any knots, and carefully refeed it.
It is entirely about respecting the immense physical forces at play there. You never operate the windlass if the breaker is constantly tripping because, as we established, that means the motor is stalling and overheating.
Right.
You keep hands, loose clothing, and long hair far away from the turning gypsy. And crucially, you always ensure the emergency manual lift handle is easily accessible. Because if a saltwater wave shorts out the electrical system completely, you need to be able to manually winch that anchor up by hand or you are permanently stuck in that bay.
We have covered a phenomenal amount of ground today. Looking back over the manuals and the forums, we've dissected the anatomy of these quick USA systems, weighing the sleek, space-saving benefits of a vertical unit against the easy accessibility of the horizontal layout.
We really went deep into the mechanics.
We did. We've traced the critical importance of preparation, why an imperfect rope-to-chain splice is a disaster waiting to happen, and how a dirty, wet anchor locker can silently destroy your motor. We explored the physics behind the art of the drop, proving that a slow, geometrically sound deployment using cockpit controls is infinitely safer and more effective than a panicked freefall.
Much safer.
And we faced the harsh reality of the saltwater environment, detailing the rigorous cleaning, electrical inspections, and safety protocols required to troubleshoot a jam without risking serious injury.
It paints a very clear picture, I think. An electric windlass isn't just a luxury accessory bolted to the bow. When it is meticulously prepared, operated with an understanding of marine physics rather than just, brute speed and aggressively maintained against the elements, it becomes a deeply trusted partner.
Absolutely.
It takes an exhausting, high-risk maneuver and transforms it into a safe, controlled routine. It provides genuine mastery over the environment.
It truly does. It removes the terror of the storm. But digging into all this technology leaves me with a final, slightly provocative thought for you to mull over.
Okay, let's hear it.
For centuries, the sea demanded absolute, raw physical strength. If you couldn't haul hundreds of pounds of heavy iron and wet, freezing rope by hand, you simply couldn't be a sailor. You were a passenger.
Very true.
But today, we have automated, remote-controlled systems like this windlass, removing that massive physical barrier, taking on all the backbreaking work with the push of a button. With technology leveling the physical playing field, how might this kind of marine engineering completely change who gets to be a sailor in the modern age?
Wow. That's a profound shift to think about. It suggests a total democratization of sailing, opening up the oceans to people of diverse ages, physical abilities, and backgrounds who would have been historically excluded from the helm.
It changes the entire demographic of the sea. So the next time you picture that boat tossing violently in the bruised plum storm, and you imagine that single sailor confidently securing the vessel, realize that the sailor doesn't need to be a heavyweight bodybuilder anymore. They just need to understand the powerful, silent partner on the bow.